Hello students, welcome. In today's lecture, we are going to learn some fundamental ideas and basic concepts of binomial theorem. So, till the last lecture, we have finished the calculus completely, and now you have to practice and you have to develop problem solving skills. And today, we will lay some foundation for the chapter of binomial theorem. Generally, students find this chapter to be one of the difficult chapters. But if you understand the pattern, and if you put little bit of hard work, this chapter could be easy for you. Now, when it comes to questions that are coming from this chapter, generally we get less questions from this chapter in both mains and advanced, but this chapter is important because this chapter has other applications, especially in permutations, combinations and probability. And the questions from this chapter may not come directly, but they come indirectly by mixing other chapters like sequence and series and permutation, combination and probability. Okay. So, that is why it is actually very important chapter even for your future also. Okay. Shall we start? So, basically we will start from fundamentals, ekdam from zero level fundamentals we will start, and then we will go on to build big concepts also. Okay. So, let us start from our school idea. Okay. So, many of you may not have studied binomial theorem earlier. So, I am starting from very basics. Okay. So, first is factorials. What is a factorial? So, we can define factorial as the product of all natural numbers starting from 1 till n. So, for example, if I want 4 factorial, starting from 1 till 4, we have to take product of all 4 numbers, and these must be natural numbers, remember this. So, 4 factorial is 24, we have understood this. Similarly, we can also write 5 factorial, 6 factorial and so on till n factorial we can write. And also if you observe, 0 factorial is 1. Now, do not get into the proof of this 0 factorial because the proof is of higher standard mathematics. You will not be able to understand that at this level, but we can understand that, we can remember that 0 factorial is always 1 for calculation purpose. Okay. So, now looking at these factorials, for example, if you look at this 5 factorial, in 5 factorial, 4 factorial is also already present. So, we can write 5 factorial as 4 factorial into 5. So, in general this gives you idea that n factorial can be written as n into n minus 1 factorial. Similarly, it can also be written as n into n minus 2 into n minus 1 into n minus 2 factorial, we can also write it like this. So, this way we can break down the factorial, okay. But product of 2 different factorials cannot give you another factorial. Remember this, that if there is one n and if there is, let us say, some m, this cannot give you some other factorial. Unless these n and m are only 1 and 2, only these cases may give you the result, which is like 1 factorial into 2 factorial can give you 2 factorial, but this cannot be true if the numbers are greater than 2. Okay. So, this is basic idea of the factorials. We have understood factorials. Now, let us move on to the basic understanding of the nomials. Okay. Now, if I say monomial, it means there must be only one term. Nomial means terms. Okay. So, if I say monomial, it means only one term. For example, 2x is a monomial, the number 4 is a monomial, 3x by y is a monomial. Okay. Now, number of variables that are present need not affect the name. Okay. So, there can be any number of variables, there could be only constant also. Okay. So, monomials means only one term involving. Okay. What about binomials? Binomials means two terms must be involved. For example, a plus b is one binomial, x square y plus z is one binomial, and like this we can generate many binomials. So we can also have terms in the denominator also. This is also one binomial. Also we can just have sum of two numbers. 2 plus 3 is a binomial. Even though 2 plus 3 is 5, we can still call this as a binomial. Okay? So binomial means two terms. What about trinomial? Three terms. And more than three terms if we have, we call it as multinomial. In fact, all trinomials starting from trinomials onwards, all terms are called as the multinomials. Okay? Now you might be confused with the term polynomials also. In fact, whether it is monomial, binomial or trinomial or multinomial, all of them are called as the polynomials. Okay? So all these will get qualified into polynomials, but when it comes to multinomial, we only take the terms involving more than three terms. Okay? So here we have understood what are the nomials. Now let us look at the idea of the binomial theorem. So binomial theorem or binomial expansion, this talks about binomial raised to some power which is natural number. Okay? So if we have binomial in the base and there is a power which is a natural number, then it is the expansion is called as the binomial theorem or binomial expansion. So to understand binomial expansion, let us observe some pattern. Okay? So for example, if we take, let us say, a plus b raised to 0, we are going to get 1, right? So if we take a plus b whole raised to 1, it is going to be a plus b. If we take a plus b whole square, it is going to be a square plus 2ab plus b square. You already have idea of these. So let me just write one more term. So a plus b whole cube is going to be a cube plus 3a square b plus 3ab square plus b cube. Okay? So now these are the terms. These are basic expansions that you have learned in school. Now let us say we want to generate an expansion for a plus b raised to 4. Then we may have to multiply a plus b whole cube and a plus b, or we may have to square the a plus b whole square. But if you want to find, let us say, a plus b whole raised to 100, then you may have to search for a pattern here. So here there are some observations that we can note here. What are the observations? First observation is this, that whatever is the power here, the same power is maintained, same degree is maintained for all the terms. For example, first term has degree 3, second term also has degree 3, a has degree 2, b has degree 1, but effective degree is 3. Next term also has effective degree 3. So every term is having effective degree 3. So we can say that binomial expansion is going to be homogeneous expression. That is one observation. Second observation, if you observe the powers, now the first term is having the highest power as 3, and in every term the power is going down by 1 unit. And if you check the second term, which is the b, so in the first it is having the power 0, and every time when we go from left to right, the power is increased by 1 unit. So for a, power is decreasing, for b, power is increasing, and that decrement and increment is always 1 unit. That is another pattern. So that means if you, let us say, want to write an expansion for a plus b whole raised to 4, then we can straight away make use of this pattern and write an expansion. Okay? So the first term is going to have a raised to 4, and the second term will be having a cube into b, third term will be having a square into b square, fourth term will be having a into b cube, and the next one will be having b raised to 4. So this way, by taking help of this pattern, we can write the expansion. But now what about the numbers that are coming with these a and b terms? These are called as the coefficients or binomial coefficients. So these binomial coefficients, how do we generalize them? For that there is one standard approach designed by mathematician named Pascal. Okay. So what Pascal did was, Pascal generated a triangle which will give us the binomial coefficients of these expansions. So you might have studied this in school also, I will quickly explain this. It is basically one isosceles triangle and two sides are having only ones. Okay. So for example, let us say you have built already one row. To go to the next row or next layer, you need to add the above two terms to get the below term. For example, if we add these two, we will get 2. If we add 1 and 2, we will get 3. If we add 2 and 1, we will get 3. That way, we can also generate the next layer. So for example, here these two terms will be ones, and to get the middle terms, we may have to add the above terms. So 1 plus 4 is going to give us 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. This way we can keep on generating all layers. And what are these layers? These layers are nothing but the coefficients in the expansion of a plus b whole raised to n. So the first layer you will get when n is equal to 0. So here we are talking about a plus b whole raised to n. This we will get for n equal to 1, this we will get for n equal to 2, this is n equal to 3, and this is for n equal to 4. So basically these terms are going to have some coefficients here, right? Some coefficients here, and these coefficients can be calculated using the Pascal's triangle. That is one observation. So what are the layers for this? 1, 4, 6, 4, 1. So we can say that these numbers are going to be 1, 4, 6, 4, 1. Okay. So this is the basic understanding that you may have developed in school. I have just quickly revised it. Okay. Now coming to the notation of these coefficients. We can name these coefficients as any number, let us say a0, a1, a2, a3, a4 or something, or we can also denote them as c0, c1, c2, c3, c4. C stands for coefficients, or we can also denote them using idea of NCR. Okay. So NCR basically represents the coefficients. Okay. We will come to that little later. So here we have understood what is the pattern and how are these coefficients following a pattern, and how is this Pascal's triangle helping us finding the binomial coefficients. Now let us say if we want to write the expansion of a plus b whole raised to 100, then we do not want to definitely write 100 layers here, because that is going to be hell of a task. So what do? We go for the definition of NCR. Okay. So we define NCR as n factorial by r factorial into n minus r factorial. Factorial is missing here, must be typing error. So using this formula we can get the coefficients. But how do we define these NCR here? This layer is basically for n equal to 5. Okay. So we define the terms as NC naught here. That means here n is equal to 5. So this is 5C naught, this is 5C1, this is 5C2, this is 5C3, 5C4, 5C5. Okay. So till now you can just remember them as the coefficients numbered from 0 to n, that is it. Now of course we have a formula, we will learn this formula also, but what is the logic of this formula? This we will learn in the chapter of permutations and combination. We will wait till that chapter, but until then we can write NCR using the formula. Okay. So this is the notation, it always goes from 0 till n, and how do we calculate these coefficients? That is the task of the next idea. Okay. So till now you have understood what is the expansion, how to use the pattern, and how are these coefficients denoted. Now let us look at the value. Okay. So suppose let us say we want to calculate 6C2. We want to calculate 6C2. How do we do that? 6 factorial divided by 2 factorial into 6 minus 2 factorial. Okay. Now further, when we expand this, what do we get? We are not actually expanding, we are just simplifying. So 6 factorial by 2 factorial into 4 factorial. Now we are going to expand this. So 6 factorial means starting from 1 we have to go till 6, okay, we have to take product of all of them, and then divided by 2 factorial means 1 into 2, 4 factorial means 1 into 2 into 3 into 4, okay. So now cancel out whatever are required and then you can calculate the value. But there is a pattern of the calculation also. For example, if you take the product of the first 4 natural numbers, it is actually 4 factorial. So this 4 factorial is definitely getting cancelled. So that means out of these two, r factorial and n minus r factorial, out of these two, one of them is going to get cancelled for sure with the numerator. That is guaranteed, okay. So here 4 factorial got cancelled. Now whatever is remaining, if you observe this, it is 6 into 5 by 1 into 2. This is actually telling us something. It says if you want to calculate 6c2, starting from 6, take only 2 numbers and divide that with 2 factorial. Let us say you are interested in 10c3. So 10c3 can be written like this. Starting from 10, take only 3 numbers, okay, take only 3 numbers and then divide that with 3 factorial. Now if you simplify, you will get the final value required. So when we cancel out 3 here and 2 also here, so we will get 3 into 4 into 10, which is 120, okay. So when I am cancelling, I mostly prefer not to cancel 10, because 10 is going to give us zeros at the end. So calculation wise, leaving 10s aside is going to help us in final calculation, okay. So this way we can calculate the NCR. So this is one simple idea of calculating NCR. So in general, if you want to write this kind of working formula for NCR, how do we write it? Starting from n minus 1, n minus 2, take how many numbers? R numbers. Now starting from n, what is the rth number? It is n minus r? No, of course not. It is n minus r plus 1, okay. So starting from n, if we go by r steps, the number is going to be n minus r plus 1, and we have to divide this number with r factorial, okay. So this way we will get a formula for NCR, okay. So this you can understand, and we of course we will prove these ideas in our chapter permutation combinations, okay. So till now you have understood what is NCR and how do we calculate it, okay. So I hope this is clear. Now let us look at some of the examples which are going to help us in understanding the pattern of NCR also. Suppose let us say I take NC naught, okay. So this NC naught is going to give me n factorial divided by n minus 0 factorial into 0 factorial. Now n factorial divided by n factorial into 0 factorial. We know that 0 factorial is 1 and here n factorial is luckily cancelled. So we will get 1 by 1, which is 1, okay. So NC naught is always 1, NC 0 is always 1. Let us look at NC n, okay. So here it must be factorial. So NC n is going to be n factorial divided by n factorial into n minus n factorial, which is going to give us n factorial by n factorial into 0 factorial. Now again this is going to give us 1. So we have understood that NC naught and NCN are basically 1s, which are the extreme cases in the Pascal's triangle, okay. Suppose let us say I go for NC1. So it is going to give us, if you go by the formula, so n factorial divided by n minus 1 factorial into 1 factorial. So here it can be written as n into n minus 1 factorial divided by n minus 1 factorial into 1 factorial. So n minus 1 factorial will get cancelled, we will get n, right. Similarly, we can also find out nc n minus 1, and this is also going to be exactly same as n. So in fact, we can observe that NCR is going to be NC n minus R. This is always valid statement, okay. Also, to understand this, if we look at this Pascal's triangle, this triangle is going to be one isosceles triangle. So about the middle term, if you draw a line, about this line, all the numbers are symmetric. For example, if you observe this, for example, for this one, phi c naught is equal to phi c phi, phi c1 is equal to phi c4, phi c2 is equal to phi c3, okay. So this is one pattern that you can always observe. In fact, this Pascal's triangle is actually going to give you a lot of other patterns also. You can explore all of them at a later stage, okay. So this is one idea that we have explored here, okay. So based on that, we can write a conclusion that if NCX is equal to NCY, if NCX is equal to NCY, then either X and Y are compulsorily equal or X plus Y must be N, okay. So for example, here if you observe, NCR is equal to NCN minus R. So now if you add these two, the sum is always going to be n. So that is this idea, okay. So either x must be equal to y or x plus y must be n, only then NCX is equal to NCY. So in future, if you get any question based on this idea, you can of course directly apply these two parts, okay. So this way we can understand the basics of the binomial coefficient, okay. Now let us look at the expansion now, okay. So let us say to expand for the general power, let us look at the simple powers also, okay, so that it will give us some idea and then we will go for the general term, okay. So let us say we are interested in writing a plus b whole raised to, let us say 6. How do we write the expansion? We can write it as 6c naught, a must have the highest power, plus 6c1 into a will have 1 down and b will have 1 up, okay. So b is increasing, so up, a is decreasing, so down, okay. Next term is going to be 6c2, a 1 down and b 1 up. Next term is going to be 6c3 into a 1 more down and b 1 more up. So in the same way we can write all other terms, okay. So let me just write all of them. 6c4 into a square into b raised to 4 plus 6c5 into a into b raised to 5 plus 6c6 into b raised to 6, okay. So this is the basic idea of the expansion. So now if you have understood this, now in place of a and b, even if there are other terms or other variables or other numbers, you must be able to reproduce the same pattern, okay. So let me just take that general expansion. Here I have just modified the terms just to leave that confusion element in your mind, so that if there is, even if there is confusion, you should be able to reproduce all of them. So for x plus a whole raised to n, what should be the pattern? For x, it must start from x power n and it should go down by 1 unit every time. See, x raised to n, n minus 1, n minus 2 and so on. And for a, it must start with 0, a raised to 0, and it has to go up by 1 unit every time. So a raised to 0, that means 1 here, a raised to 1 here, a square and so on till a raised to n. We have understood that. What about the coefficients? Coefficients always start with naught, that means 0, and go till n. So nc naught, nc1, nc2 and so on till ncn, okay. So this way we have understood the general expansion. Now every time whenever we learn any new concept, we have to take a pause and we have to observe the pattern there, okay. So, here we have observed the pattern of the powers, we have also observed the pattern of the coefficients. Now, what about the total number of terms? What is the pattern of the terms? We can always name the first term as T1, second term as T2, third term as T3, and the last term will be, guess, it is n plus 1. So, here in binomial expansion, if the power is n, the total number of terms are going to be n plus 1, we have observed that. And also based on this we can write general term, okay. We can of course write a general term here, we will write the general term in the next page. But understand that in any sequence or in any pattern of the numbers, we always start the first term or name the first term as T1 and second term as T2 and so on, okay. Now, we have observed that there are n plus 1 terms, that is right, and also we have observed that sum of powers of a and x in each term is equal to n, right. So, every time sum of these two powers is going to be n, and general term is, what is the pattern of the general term? You might have already observed it here, okay. So, in T3 there is a square. So, catch only one, you do not have to generalize everything, you can catch only one aspect, you generalize it, and based on that you can generalize the other terms using that relation, okay. So, here T3 has a square, T2 has a raised to 1, T1 has a raised to 0, right, Tn plus 1 has a raised to n, okay. What about T10? This is going to have a raised to 9, and T20 is going to have a raised to 19. So, Tr is going to have a raised to r minus 1, right. Of course, this is the pattern. So, here because there is this 0 which is starting from, we generally derive the general term in terms of r plus 1. So, we say that Tr plus 1 is our general term. In sequence and series, Tr is our general term, but in binomial theorem, Tr plus 1 is our general term. In sequence and series, r equal to 1 will give you first term, but in binomial theorem, r equal to 0 will give you the first term. Remember this idea, okay. And Tr plus 1 is going to contain a raised to r, right. Now, we know that both the powers x and a, the sum of the powers of these two must be always equal to n. So, if a has taken already r, then x must be having n minus r, right. And again observe this, T3 has NC2, T2 has NC1. So, that means Tr plus 1 will be having NCr. So, this way we can write a formula for the general term, okay. So, I hope you have understood the idea of the general term. Now, when it comes to the values of r here, r must be varying from 0, 1, 2, 3 and so on till n, and r must be belonging to whole numbers, okay, set of all whole numbers, okay. R must be belonging to set of all whole numbers. Now, here whenever I write this set of all whole numbers, natural numbers, integers, of course, I use this double stroke, okay. So, one student was asking this doubt. So, it is actually one general notation of international standard, okay. So, we write set of all natural numbers like this with double stroke n, okay. Set of all whole numbers is like this, set of all integers like this, also like this, okay. Set of all real numbers like this, again it is double stroked, and set of all rational numbers like this, q is also double stroked, set of all irrational numbers also like this, set of all complex numbers also has double stroke there, okay. So, in a way we can say that it is C with one extra double stroke. So, this double stroke is actually international standard, and that is how you will learn in future also, okay. So here r must be a whole number. Okay. Now can we move on? So remember that you can have 0th term, first term, second term, third term, but you cannot have 2.5th term. You cannot have 2.9 term. Okay. So the term number must be a whole number. Okay. Now can we move on? Okay. So here this is the binomial expansion. Now let us explore this a bit by changing the terms and by supplying one minus sign as extra. Suppose let us say if I put x minus a whole raised to n, then how do we derive this? In the earlier expansion, in place of a, put minus a and derive it on your own. So then you will be getting terms like this. So whenever a is having odd powers, it will carry minus sign. Whenever a is having even powers, it will carry plus sign. So here plus minus term will be alternating. Okay. So now that we have learned how to derive the general term, we can also write this in terms of the general term. So what will be the general term here? TR plus 1 will be NCR into x raised to n minus r into minus a raised to r, right? So if I put sigma over this and say that r is varying from 0 to n, it simply means that we have basically expanded the binomial theorem. Okay. So this is one notation of the binomial theorem also. Okay. Now similarly, in place of x, if I put 1, then what happens? So 1 plus x whole raised to n may look somewhat like this. Okay. Now this is one of the very standard expansions. In fact, we will be using this expansion most of the time in this chapter. Okay. Also, there is some kind of notation in books that NC naught is denoted with C naught, NC1 is denoted with C1, NC2 is denoted with C2. So we can write it as C1x, C2x square and so on. Okay. Now that I am mentioning this different notation, let me also explain this different notation for NCR. If we write an expression like this, it also means NCR. Okay. This also means NCR. Also there is this expression. If we write it like this, it also means R factorial. Okay. So some books are having this kind of notation. If you take the old books like Hall and Knight or SLONI type of books, which are very old, 100 years old or something, you may see this notation because this is the old notation, this is the new notation. Okay. And sometimes people also read NCR like this, N choose R. Okay. People also write it as N choose R. That means this idea actually comes from the combinations or permutations, that is a different chapter, but N choose R means also it is NCR. Okay. Now let us go back to the expansion. So here we have also understood that these binomial coefficients can also be written this way, C0, C1, C2 and so on. Okay. Next, if we have let us say 1 minus x whole raised to n, so of course we are going to follow the same pattern here. So whenever power of x is odd, it will carry minus sign, whenever power of x is even, it will carry plus sign. So these are some simple expansions. Okay. Can we move on now? Okay. Next, these are some properties of the binomial coefficients, or also we can also call them as basic properties. So the first one is, what happens when we divide one binomial coefficient with other binomial coefficient? But remember that everything at a fundamental level in mathematics is a number, even a variable is a number. So we can any time divide one number with another number. Okay. So how do we do this? Let us say I will derive at least two properties for you and remaining you can derive on your own. So we can take the LHS like this. Numerator can be written as n factorial by r factorial into n minus r factorial, and denominator can be written as n factorial divided by r minus 1 factorial into n minus r plus 1 factorial. From n, if we subtract r minus 1, we will get n minus r plus 1. Now observe these and tell me if there are any terms which are getting cancelled. So of course n factorial is getting cancelled, okay. So we can cancel this out. Now out of this r factorial and r minus 1 factorial, which is smaller? R minus 1 is smaller. So whatever is the smaller will get cancelled, okay. So out of these two, r minus 1 factorial will get cancelled. So what remains is r. So in the denominator of the numerator, r remains. Similarly, out of these two, n minus r and n minus r plus 1, out of these two, which is smaller? N minus r is smaller. So smaller one always gets cancelled when it comes to factorials. So we will get denominator of the denominator as n minus r plus 1. Now when we simplify this, we are going to get this term, which is nothing but the RHS, okay. So this way we can prove it. So I think it's very silly and simple. So we don't have to learn much from this, but you can remember the result, or you may not even remember the result, it does not matter. You should know how to handle it, that's it, okay. Let me just erase it, go on to the next property. But this is very, very important property, okay. So here it says NCR plus NCR plus 1 is always n plus 1 CR plus 1. This we can try to prove. If you are interested in proving, you can take a pause and then prove it and then look at the solution, okay. So I am taking LHS here. LHS can be written as n factorial by r factorial into n minus r factorial plus n factorial by r plus 1 factorial into n minus r minus 1 factorial, okay. Now let us see if there are any terms which can come common. In the numerator we can see that n factorial can get common, and in the denominator if we observe, whatever is the smaller will get common, okay. So for example here we can write it as n factorial is taken common, and out of these two r is smaller, so r factorial is taken common, and out of these two n minus r and n minus r minus 1, n minus r minus 1 is smaller, so we can write it as n minus r minus 1 factorial. Now if we check what are the terms which are remaining. So here what remains is 1 by n minus r from the first term. From the second term what remains is 1 by r plus 1, okay. So now further if we just simplify this term, what do we get? R plus 1 plus n minus r divided by n minus r into r plus 1, right. So here luckily r is getting cancelled. So what is remaining? N factorial into n plus 1, this is in the numerator, okay. So in the denominator we have r plus 1 into r factorial and another term which is n minus r into n minus r minus 1 factorial. Now if you observe, n plus 1 into n factorial is n plus 1 factorial, and r plus 1 into r factorial is r plus 1 factorial, and here it can be written as n minus r factorial, okay. So we can further write it this way. So numerator is n plus 1 factorial, denominator has r plus 1 factorial, but n minus r can be written this way. N minus r can be written as n plus 1 minus r plus 1 factorial, okay. So now you can notice that it is nothing but n plus 1 c r plus 1, okay. So we did so much hard work to prove this, but there is not much hard work, it is only about writing, but graphically speaking, the terms are big, that is why it may look big, but it is actually a simple calculation. That is why students find it difficult, find this chapter to be difficult, because numerically it may look big, because graphically it may look big terms, but they are not that big. Okay. So here if you observe clearly, we can say that, let us say 4c2 plus 4c1 can be written as 5c2, or in other words, let us take another example, 5c2 plus 5c3 can be written as 6c3. Okay. So this is basically the property. Now, have we not seen this property earlier? Of course, we have seen this in Pascal's triangle. In Pascal's triangle, the property based on which we built the triangle is basically this property. That is what makes this very important property. Now, let us look at this in the Pascal's triangle. Okay, so here this term is 4c1, this is 4c1 and this is 4c2. Okay, so when we add 4c1 and 4c2, we must be getting this 5c2. Similarly, let us say I add 5c2 and 5c3, I will be getting 6c3 here. So if you start from the beginning, this is 6c0, here 6c1 and here 6c2, this is 6c3, this is 6c4, 6c5 and 6c6. Okay. So here you can observe that it is actually the property based on which Pascal's triangle is built. Okay. So now you have understood this second property, which we use mostly in problem solving. So that is why this is very important property. Okay. So you can take a snapshot or you can just make a note. Okay. So now there are two more properties. These properties also you can derive based on the same idea. Okay. For example, here it says NCR is equal to n by r into n minus 1 c r minus 1. Okay. So we can also write it as n into n minus 1 by r into r minus 1 into n minus 2 c r minus 2. So these properties also can be derived using the earlier idea. For example, if you look at the earlier idea, this is exactly same as the earlier idea. In place of r, in place of n, if you put n minus 1 and try to simplify it, you may get this. Okay. Or you can also expand it, take terms common and then prove it. But every time you may not remember these ideas. You know, you don't need to remember. If you just remember the way we proved all of them, you can derive them on your own in the exam. It will not take much time. It may take roughly 5 to 10 seconds in the exam. Okay. But you have to master that technique. Okay. Similarly, there can be another form like this. Okay. So these forms you can derive on your own. Okay. So now let us move on to some of the problem solving ideas. Okay. So basically today we have not learned much. We have learned what is binomial theorem, how do we expand, what is the pattern and how do we generalize that pattern, what are the basic properties of binomial coefficients. Now let us look at some of the problems. Okay. So there is this first problem. So here find the 11th term in the expansion of 3x minus x by root 3 whole raised to 20. So how do we start a problem? To start a problem, look at this question talks about the 11th term. So number is given to a term. So if term's number is mentioned, what is the best way to tackle the problem? To generalize in terms of the general term. So we have to start our problem with the general term. In general, what is the general term? It is going to be TR plus 1, right? So for this, we can write the general term like this. TR plus 1 is going to be, it is going to have NCR, what is the power? 20. So it will have 20 CR, it is clear. Now what about the power of the second term? See, I have remembered a pattern. You can also design your own system. Okay. So, I always remembered that the second term out of those two binomial terms, the second term will be having the power r. So, which means this minus 1 by x root 3 is going to be having power r. So, that means first term will be having power n minus r. So, n here is 20. So, 3x raised to 20 minus r should be there, right. So, we have got the expression for general term. Now, what is the question? We have to find the 11th term. That means T11 we want. So, if we are interested in T11, what should be the value of r? R should be 10, right. So, put 10 here and get the answer. Okay. So, in fact, in these type of questions, when you crack r equal to something, you have cracked the 50% of the problem. Okay. So, now whatever is the remaining required term, we can calculate it by substituting r equal to 10. So, this will come out to be 20c10 into 3x raised to 20 minus 10 and minus 1 by x root 3 raised to 10. Okay. So, further we can simplify it. So, 20c10 into 3 raised to 10 into x raised to 10, because 20 minus 10 is 10, okay, and then minus 1 raised to 10 divided by x raised to 10 root 3 raised to 10, x raised to 10 got cancelled, and further we can write it as 20c10 into 3 raised to 10 by 3 raised to 5, others minus 1 raised to 10 is plus 1, root 3 raised to 10 is 3 raised to 5. So, further we can write it as 20c10 into 3 raised to 5. Okay. But here, if you want to further simplify 20 raised to 10, definitely it is not recommended, because this number is going to be too big. Okay. So, in this chapter we can leave the answers like this. Okay. So, whenever you arrive at the answer where 20c10 like this kind of numbers are mentioned, you can just leave them like that. Okay. So, this way we can solve the problem. Okay. So, just quickly take a snapshot. Okay. Can we move on? Suppose in the same question, let us say there is a slight variety. Let us say if the question is, find the sixth term from the end. That means we want the sixth term from the last term. So, how do we do this? In this expansion, total how many number of terms will be there? 21 terms will be there. So, that means the last term is going to be T21. What about the next term? Last but one term is going to be T20. So, like this if you go on, what will be the sixth term here? It is going to be T16, right. This is our sixth term from the end. So, if we are interested in T16, our R must be 15. So, once if you crack R, you have solved the 50% of the problem. Okay. So, by substituting R equal to 15 here, you can calculate the required term. Okay. So, these are some basic ideas of finding the term if the number of the term is mentioned. Let us look at a different variety. Here, questions are about finding the coefficient of something. So, here it is not based on the term number, it is based on the power of x. So, how to deal with them? We start with the same idea of general term. Okay. So, here if I write general term, TR plus 1 will be 9CR into 3 by 2 into x square raised to 9 minus r into minus 1 by 3x raised to r. Okay. Now, further we cannot leave it like this, because this question is different. We are interested in powers of x. So, we have to separate x. So, let us separate x and constants separately. Okay. So, here when I separate x and constants, what do we get? We get 9CR into 3 by 2 raised to 9 minus r into minus 1 by 3 raised to r. And what about the powers of x here? So, in the numerator, we will have x square raised to 9 minus r. This is going to be x raised to 18 minus 2r, right? A raised to m whole raised to n is a raised to mn. And also 1 by x raised to r is going to be 1 by x raised to r. Now, when we divide the second with first or first with second, we are going to get x raised to 18 minus 3r. Okay. So, here we separated x and we separated the numbers. Now, this 9CR is basically the binomial coefficient, and if we combine all these terms, it is going to be the coefficient. Okay. So, I hope you understand this. There is a difference between general coefficient and binomial coefficient. So, binomial coefficient means only NCR form, but along with that, if there are constants, all of them must come in the coefficient, which is a general coefficient. Okay. So, here only coefficient of x raised to 6 has to be calculated, which means we are talking about the overall general coefficient. Okay. So, till here we have generated the general term. Now, let us attack the question each one by one. Okay. So, the first one is we have to find coefficient of x raised to 6. So, that means our power must be equal to 6. So, what is our power here? 18 minus 3r is our power. So, this 18 minus 3r, this must be equal to 6. So, that is the first case. So, 18 minus 3r is equal to 6. From here we will calculate r and then we will calculate the question. Okay. So, how do we do this? 18 minus 6 is going to be 3r, 18 minus 6 is nothing but 12. So, r equal to 12 by 3, which is 4. We got the value of r. So, now we can further proceed to solve the question. Okay. So, what would be the coefficient of x raised to 6? It is going to be, we have to put r equal to 4 here. So, 9c4 into 3 by 2 raised to 9 minus 4 into minus 1 by 3 raised to 4. Okay. So, further we want to simplify this. So, what do we get? 9c4 will be 9 into 8 into 7 into 6 divided by 1 into 2 into 3 into 4, right, into it is 3 raised to 5 here, 2 raised to 5 here and 1 by 3 raised to 4 here. So, let us see if there are any terms which may get cancelled. So, 2 and 4 will get cancelled with this 8 completely, and there is 1 3 here, 3 raised to 4 here, 3 raised to 5 here. So, this will get cancelled with these 3's. So, what is remaining is 9 into 7 into 6 divided by 2 raised to 5 or 9 into 7 into 3 divided by 2 raised to 4. You can further calculate or leave it like this. In fact, you do not even have to simplify further, you can just leave it right here. Okay. So, this way we can calculate the coefficient. So, I hope you have understood the process. Now, let us look at the next term, next problem, next case, sorry. So, this is about coefficient of x raised to 10. So, how do we calculate this? Again, we have to equate the power to 10. So, let us say if I equate this 18 minus 3r power to 10. So, what do we get? We get 3r is equal to 18 minus 10, which is 8, which means r is equal to 8 by 3, which is same as, let us say, roughly 2.67. Now, tell me if this term exists or not, because r must be a whole number, that is the first condition. So, because r must be a whole number and here 2.67 is not possible, we cannot have term which is having the term number as 2.67. Either you have second term or you have third term. You cannot have 2.6 term. Okay. So, this means the term that we are looking for does not exist. Okay. The term that we are looking for is not in this expansion, which also means the coefficient of x raised to 10 is going to be nothing but 0. Okay. So, that means if there is no such term, we can conclude that the coefficient has to be 0. Okay. So, I hope you have understood this idea also. Let us look at the next part. So, next part is about term independent of x. What is the meaning of independent of x? If you look at this expansion, look at the general term. In every term, there is some or the other x, right? Because x is there and power is there. So, if we are talking about term independent of x, it means x must be completely vanished in that term, which means the power of x must be 0. We can also call it as the constant term. Okay. So, this question can also come as find the constant term. Okay. But in both the cases, analysis must be same. So, what do we have to do? We have to equate the power to 0. Now, when we simplify, what do we get? R equal to 6. So, in the general term, if we put R equal to 6, so it will become T7 and that is going to be 9C6 into 3 by 2 whole raised to 9 minus 6 into minus 1 by 3 raised to 6, and of course, power of x is 0. Okay. So, when we simplify, what do we get? Here we get 9 into 8 into 7 divided by 1 into 2 into 3. I did not take 6 terms, I took only 3 terms. Why? Because 9C6 is same as 9C3. Okay. So, I use this idea directly. Okay. 9C3 is same as 9C6. Okay. So, I calculated 9C3 here into 3 raised to 3 divided by 2 raised to 3 into 1 by 3 raised to 6. Okay. So, now let us simplify this. So, there is 2 cube here, there is 2 here, that means 2 raised to 4, which is 16. So, when 8 gets cancelled, we will be having only 2 here. So, only 2 remains there, and there is 3 raised to 6. When this gets cancelled, we will get only 3 cube here, and there is this 3 square here. So, when that gets cancelled, we will be left with only 1 3 square here and 1 2 here and 1 7 here. Okay. So, the value is going to be 7 by 18. This is our constant term. I just calculated it because the numbers are small numbers. That is why I took the expansion as power 9, okay, because I wanted the calculation to be simple. But if the power is big, then of course you are going to have lot of terms which are going to give you bigger calculations. Okay. So, here if you notice, I have hit only 2 patterns. One is where the number of the term is given, the other is where we are interested in the powers of x. Okay. So, in both the cases, our analysis starts from the general term and then we proceed. Okay. So, we have also have lot of problems, but probably maybe in the next lecture we will take up those problems and then we will learn some more new concepts and some more problems. Okay. So, I hope you guys are enjoying the lectures. Please share the feedback on the app, and if you have friends who need these study, and especially if you like the overall academics of YepMaster and if you like the study content and teaching content, you definitely can recommend to your friends also. Okay. So, we will close the lecture at this point. We will meet again in the next lecture with more new techniques and ideas. Until then, have a great learning day. Learning shall never stop.